Calculus can really be split into two main parts, derivatives and integrals, with the tail end of Calc BC covering something called series, which will build on both ideas. But for now, the main focus of the first, I say third of this school year will be on something called the derivative. In previous videos, we talked about the idea of average speed being the same as average rate of change, or physically speaking on a graph, the slope of a secant line. And so we're going to take that information and see if we can use that information to help us build the idea of a derivative, which really is just instantaneous speed. Now, I'm going to also throw in the idea of velocity. Velocity is speed with direction. So if I'm moving forward, I have a positive velocity, which is speed with a positive sign in front of it. And then if I'm moving backwards, that's a negative velocity. Same idea applies for horizontal particle motion, where if the particle moves to the right, it's positive velocity. If it moves to the left, it's negative velocity. So now let's start with the idea that we had developed in the previous video of the rate of change being the slope of the secant line. Let's go ahead and generalize that. So on your paper, you should have the graph of this parabola in the first quadrant. And we're going to generalize 2 points on this graph. And what I'll do is and the parabola doesn't have to be specific to the one that you see here. Just have a general shape going on and pick any 2 points. The one on the left, let's call that an arbitrary x value. The point over right of that, we're going to move h unit over. So this length right here is h units. And we're going to call this coordinate point x for the x that we started with plus h units. And if this function is f of x, then the y values would be f of x and f of x plus h. And again, these are general values. They don't have to be any specific points on the curve. So from here, let's start with what we did in the previous video and example. We're going to find the slope of the secant line. So m for slope, secant line, is equal to, and slope using algebra 1 is change of y over change of x. So to find the line, which I will draw in yellow, connecting this point and this point, to find that slope, we would then use the change of y being the y coordinates that you see here, f of x plus h and f of x. The x values will be x plus h, x. So putting that together, we have on top, f of x plus h minus f of x is the change in y all over x plus h minus x. And so that expression can be simplified on the bottom to mean that the x's cancel and we have just h left over. So another way of describing this is also, besides the slope of the secant line, is called the difference quotient. And I hope that you did see that in pre-calc honors, that you worked on simplifying the difference quotient. If not, we will have some review on that, and I'll talk to you guys in length about what it is you have to be able to do with that. So how is this? So that's assuming that you have a time at x and then another time sometime later on at x plus h, you're able to find the average speed or the average rate of change using the slope of the secant line. How is it then that, and I will erase this in a minute as soon as I just describe this, how is it that I am able to identify what my instantaneous speed is at this moment in time, or say at this, or at this? So instantaneous rate of change we're going to describe as the slope of the a slope of the tangent line. So the slope at a single point. And so the question is, well, how am I supposed to find the slope with just one coordinate point? And so we add this idea of a limiting factor process into the secant line. What if I take the point, and let me erase these red tangent lines. What if I take the point that is on the right and I slowly move that point so that the secant line that is formed becomes closer and closer to this point right here. And so again, take this point and close in that distance so that it gets closer and closer to this point here. Okay, so that's where we introduce a limit to it. And so this distance that I'm closing in on is actually this distance here. So if I allow this distance to move to close in and for h to get really, really small, I'm letting h go to 0. Okay, so let's go ahead and put that into a limit. So the slope of a tangent line is then what we define as a derivative. And so the definition of the derivative here will be the limit as h approaches 0. So we close in on that gap of this difference quotient. And here is our definition of the derivative. I'm also going to describe the definition of the derivative using a different or alternate take on the 2 points that I have defined initially. Instead of x and x plus h, I'm going to use x and a. So in the next video, I'll go ahead and do that.